Welcome back, everybody. Today, we're going to be taking a deep dive into algebraic K-theory.
All right.
And you guys sent in some really intense research papers and reports.
Oh, wow.
Yeah, there's mentions of Waldhausen's S-dot construction,
Okay.
spectral categories, even stable infinity categories. And honestly, I'm a little intimidated,
Yeah.
but I'm also super curious.
Right.
So let's break this down together.
Yeah.
What is algebraic K-theory like at its core?
So it's kind of like a mathematical detective tool
Nice.
that helps us uncover hidden structures and patterns within mathematical objects. Think of it like this. You have a complex machine,
Okay.
and K-theory lets you break it down and see how all the gears and levers work together,
Okay.
even revealing connections you wouldn't have guessed were there.
Okay, I'm intrigued. So it's not just about crunching numbers.
Right.
It's about understanding the underlying blueprint of a mathematical object.
Exactly. And one of the most fascinating aspects of K-theory is how it acts as a bridge between different areas of mathematics. The research you provided keeps mentioning K-theory as a functor,
Right.
which essentially means it translates concepts between different mathematical languages.
Okay.
It's like finding a Rosetta Stone
Wow.
that allows us to decode the secrets
Okay.
of various mathematical universes.
Okay, I'm starting to see how powerful this could be.
Yeah,
But how does this translation actually play out?
sure.
Can you give me a concrete example from the research?
Absolutely. One paper dives into the algebraic K-theory of a scheme,
Okay.
which, believe it or not, can be characterized as a specific kind of blueprint called the initial sheaf of spectra.
Okay.
This blueprint essentially provides a set of instructions for constructing the K-theory of that scheme.
Gotcha.
It's like having a master key that unlocks a whole new level of understanding about these complex mathematical objects.
Wow, that's pretty mind-blowing.
Sure.
So it's not just about analyzing existing objects. It's about building new understanding from the ground up.
Precisely. And here's where it gets even more intriguing.
Okay.
The research also touches upon negative K groups,
Okay.
which might sound a bit like something out of science fiction.
Right.
These groups are fascinating because they reveal information about a mathematical object that regular K groups don't capture.
Okay, now you've really got my attention.
Right.
What kind of information we're talking about?
So imagine you're looking at a sculpture.
Okay.
The regular K groups might tell you about its shape and form, but the negative K groups reveal hidden internal structures and tensions that influence the sculpture's overall stability.
Wow.
They provide a completely different perspective on the same object, adding another layer of depth to our understanding.
That's a great analogy. It's like we're not just seeing the object.
All right.
We're understanding its underlying mechanics. And I'm guessing this has some pretty significant implications, right?
You're absolutely right. One of the papers highlights a surprising connection between the negative K groups of a connective ring spectrum and the K groups of its underlying ring. This suggests a hidden symmetry, a kind of mathematical mirror image between these seemingly disparate concepts.
So we're not just talking about translating between different mathematical languages anymore.
Right.
We're uncovering hidden relationships.
Exactly.
And symmetries within those languages themselves.
Exactly. And the more we explore K-theory, the more we realize that these connections run far deeper than we initially imagined.
This is already more fascinating than I could have imagined, and we've only just scratched the surface.
Yeah.
But before we go any further, let's take a closer look at some of those what moments from the research you mentioned earlier.
I'm happy to delve into them. One that particularly caught my eye involved a proof for a theorem in algebraic K-theory. Now, the specifics of the theorem are a bit technical, but what's fascinating is the story behind the initial proof.
Right.
It relied on something called Karubi periodicity, which is a pretty advanced concept. But the point is, even brilliant mathematicians sometimes hit roadblocks and need to come up with creative solutions to overcome them.
Okay, I'm all ears.
Yeah.
What was the roadblock in this case, and how did Karubi periodicity provide a workaround?
So the mathematicians were struggling to prove a certain property of K-theory using the tools they had available. It was like trying to fit a square peg into a round hole.
Right.
Then they stumbled upon Karubi periodicity, which essentially created a new tool, a way to transform the problem into something they could solve with their existing methods.
So it's a bit like finding the right wrench to loosen a stubborn bolt.
Exactly.
You need the right tool for the job.
And this example highlights the human element of mathematics. It's not just about cold, hard logic.
Right.
It's about creativity, ingenuity, and sometimes a bit of luck.
I love that.
Yeah.
It reminds us that even in a field as complex as mathematics, there's still room for moments of, aha.
Right.
And even a little bit of, wait, what?
Absolutely. And those moments are often the most exciting.
Yeah.
Because they lead to breakthroughs and new discoveries.
Okay, I am officially hooked. But let's not get ahead of ourselves. Before we get lost in the excitement, you mentioned another, what moment in the research?
Yeah.
Something about Motivic filtrations, right?
Yes.
Okay.
That one is particularly interesting.
Okay.
It's all about peeling back the layers of a mathematical object,
right,
like an onion,
okay,
to reveal deeper and deeper levels of complexity within its structure.
Okay, this sounds fascinating, but honestly, Motivic filtration sounds pretty intimidating.
Okay.
Can you break it down for me and for our listeners in a way that won't make our heads spin?
Of course. Imagine you have a beautiful, intricate tapestry.
Right.
At first glance, you see the overall design and colors.
Uh-huh.
But as you look closer,
right,
you notice subtle details, different types of threads, and even hidden patterns in the weaving.
Okay.
That's what Motivic filtrations do for us in mathematics. They allow us to zoom in and examine the fine details of a mathematical object, revealing hidden structures and relationships that we might otherwise miss.
Okay. I'm starting to get a clearer picture. It's like we're using a magnifying glass.
Precisely.
To uncover the secrets hidden within a mathematical masterpiece.
And sometimes these filtrations reveal surprising connections between seemingly unrelated concepts.
Okay.
For example, the research mentions the even filtration, which in certain cases unexpectedly recovers the information contained in the Motivic filtrations.
Wait, so it's like finding a shortcut through the layers of the onion.
It's as though there are secret passageways and hidden symmetries within these mathematical structures that we're only beginning to understand. And the deeper we dive into K-theory, the more we realize just how interconnected and mind-bogglingly complex the mathematical universe truly is.
Wow, this is all so much more than I ever expected. Algebraic K-theory isn't just about numbers and equations.
Right.
It's like a whole new way of seeing and understanding the world around us.
It really is.
All right, I'm ready to dive back in. Before the break, we were talking about how algebraic K-theory could potentially be used to analyze complex systems outside of pure mathematics.
Right.
That's a pretty bold claim. Can you elaborate on that?
It's definitely an area ripe for exploration. Remember how we talked about K-theory's ability to reveal hidden structures and connections?
Yeah.
Well, think about the complex systems we encounter in fields like physics, biology, or even social networks. They're all made up of intricate interactions and relationships that are often difficult to grasp.
Okay, I see where you're going with this. You're suggesting that K-theory could act as a sort of universal decoder for these complex systems, helping us to understand how they work at a fundamental level.
Exactly. Take physics, for example.
Okay.
One of the biggest challenges is unifying different theories, like quantum mechanics and general relativity, into a single framework. Perhaps K-theory, with its ability to connect seemingly disparate concepts, could offer a new perspective on this problem.
That's a fascinating thought. So instead of trying to force-fit different theories together, we could use K-theory to uncover a deeper underlying structure that connects them naturally.
Precisely. It's like instead of trying to solve a jigsaw puzzle by jamming pieces together, we use K-theory to reveal the underlying picture that guides how the pieces actually fit.
I love that analogy. It really highlights the potential power of K-theory to change the way we approach scientific problems.
Yeah.
But let's get specific. You mentioned biology and social networks. How could K-theory be applied in those fields?
Well, think about the intricate networks of interactions within a cell, or the complex dynamics of social groups. These systems are full of feedback loops, dependencies, and emergent behaviors that are notoriously difficult to model.
Yeah.
K-theory could provide tools to analyze these networks, identify key connections, and maybe even predict how the system might evolve over time.
So it's like we're using a mathematical lens to zoom in on the intricate wiring of these complex systems, seeing how each element influences the others.
Yes. And by understanding those connections, we might gain insights into things like how diseases spread, how ecosystems maintain balance, or even how social movements gain momentum.
This is truly mind-blowing. It's like K-theory is opening up a whole new frontier of scientific exploration, allowing us to see the world in a completely different way. But I have to ask, are there any concrete examples of K-theory being used in this way?
Right.
Or is it mostly theoretical at this point?
It's still early days, and much of the work is theoretical. However, there are some intriguing hints from the research you provided. Remember those negative K groups we discussed?
Yes.
Well, it turns out they have connections to connective ring spectra, which are mathematical objects that pop up in areas like algebraic topology and homotopy theory.
Okay, those terms are still a bit over my head, I have to admit.
Sure.
But you're saying there's a link between this abstract concept of negative K groups and fields that have applications in the real world.
Exactly. And those fields, like algebraic topology, are already being used to analyze things like data analysis, computer graphics, and even robotics.
Wow.
So the fact that there's a connection between these fields and K-theory suggests that there might be a pathway to apply K-theory concepts in those areas as well.
This is so exciting. It's like we're uncovering a hidden network of connections between seemingly disparate fields, and K-theory is acting as the central hub. But let's shift gears for a moment. Earlier you mentioned that K-theory could also provide insights into how mathematical concepts themselves are connected.
Yes.
Can you elaborate on that?
Of course. One of the most fascinating aspects of K-theory is its ability to unify different branches of mathematics.
Okay.
Remember how we talked about K-theory acting like a Rosetta Stone translating between different mathematical languages?
Yeah.
Well, it turns out that it can also reveal hidden symmetries and relationships within those languages.
Okay, so it's not just about translating between languages, it's about understanding the underlying grammar and structure that governs those languages.
Exactly. It's like discovering that different languages share a common root.
Right.
A deep structure that connects them in unexpected ways. One example from the research is the connection between Motivic filtrations and the even filtration.
Okay.
Remember how we talked about these filtrations as being like peeling back the layers of an onion to reveal hidden complexities?
Yeah.
Well, in certain cases, the even filtration unexpectedly recovers information contained within the Motivic filtration.
Wait, so it's like finding a shortcut through the layers of the onion?
Yes. It's as though there are secret passageways within these mathematical structures that connect seemingly distant concepts.
Wow.
And these connections hint at a deeper level of order and interconnectedness within mathematics itself.
This is incredible. It's like we're not just exploring the vast landscape of mathematics.
Right.
We're mapping out the hidden pathways and connections that make it a unified whole.
Exactly.
But I have a question.
Sure.
How does this kind of abstract theoretical work actually translate into practical applications?
Okay.
It all sounds very fascinating.
Yeah.
But is there a real-world payoff?
That's a great question. And it's one that mathematicians are still grappling with. The beauty of pure mathematics is that it often leads to unexpected breakthroughs in other fields, even if the initial applications aren't immediately obvious.
Right. So it's a bit like planting seeds that might blossom into something amazing down the road.
Exactly. Take number theory, for example. It was once considered a purely abstract field with no practical value. But now it forms the basis of modern cryptography, which is essential for secure communication and online transactions.
Yeah.
Who knows what amazing applications await us as we delve deeper into the mysteries of K-theory?
I'm starting to think the possibilities are truly endless. But before we get too carried away with speculation, let's take a moment to recap what we've learned so far.
Okay.
We've seen how algebraic K-theory can reveal hidden structures and connections not just within mathematical objects, but also between different fields of study. And we've started to glimpse the potential for K-theory to revolutionize the way we approach complex systems in the real world.
Indeed, it's been quite a journey so far.
But I feel like there's still so much more to explore. So before we wrap up this deep dive, I want to hear your final thoughts on the big picture. What does all of this mean? Where does it all lead? What questions should we be asking as we continue to explore this fascinating field? That's the million-dollar question, isn't it? Where does all this amazing, mind-bending knowledge lead us?
Well, I think one of the most important takeaways is that we shouldn't underestimate the power of abstract thought.
Right.
Algebraic K-theory might seem incredibly esoteric, but as we've seen, it has the potential to unlock deep insights into the nature of mathematics itself, and even shed light on complex systems in the real world.
So you're saying that even though we can't always see the immediate practical applications,
Right.
pursuing knowledge for its own sake can lead to unexpected breakthroughs down the road.
Absolutely. Think about the history of science.
Okay.
So many groundbreaking discoveries emerged from seemingly unrelated fields of study.
Right.
Who would have thought that studying the behavior of light would lead to the development of lasers?
Right.
Or that exploring the properties of electricity would give rise to the digital age?
That's a great point. It's a reminder that knowledge is interconnected in ways we can't always predict.
Right.
And perhaps algebraic K-theory, with its ability to bridge different areas of mathematics and even connect to other scientific disciplines, is poised to be one of those unexpected game changers.
I believe it has the potential to be just that. But as with any new field of exploration, there are still so many unanswered questions.
Yeah.
For example, how can we develop more intuitive and accessible ways to understand and apply K-theory concepts?
Right.
Can we create new computational tools to leverage its power for analyzing real-world data?
Okay.
And perhaps most importantly, how can we foster collaboration between mathematicians and scientists in other fields to explore the full potential of K-theory?
Those are fantastic questions. It sounds like we're just at the beginning of a very exciting journey of discovery.
It really does.
And I have a feeling that the more we learn about algebraic K-theory, the more we'll realize just how much we don't know.
That's the beauty of it. Every answer we find leads to even more questions, pushing us to expand the boundaries of human knowledge.
Well, I, for one, am incredibly inspired by this deep dive. It's made me realize that even the most abstract concepts can have profound implications for our understanding of the world. And who knows? Maybe one of our listeners will be the one to unlock the next major breakthrough in K-theory.
I certainly hope so. The future of this field is wide open, and the possibilities are truly limitless.
On that note, I think it's time to wrap up our deep dive into algebraic K-theory. To our listener, thank you for joining us. Keep exploring, keep learning, and keep those aha moments coming. Until next time, happy learning.